All right, we can get started. We have a long list of speakers here. Oh, do we? Let's see. Oh, yeah, a couple others. Well, did it get shortened? I only see two names now. Oh, no, a couple others. Okay. The next talk is Net2Brain, a toolbox to compare artificial vision models with the human brain responses. The speakers are Dominique Bersch, Dwivedi, Vilas, Sichi, Roig, and Wolfgang. Presenting will be Bersch.
All right, so hello everyone, hello esteemed colleagues. My name is Dominique Bersch and I'm happy to present you to Net2Brain, our toolbox to compare artificial vision models with human brain responses. Today I would like to introduce you to Net2Brain and demonstrate the potential of our toolbox and how it could maybe benefit you. So let me first recap some of the background regarding this research, after which I will happily introduce you to Net2Brain. Then I would like to show you a little live study using Net2Brain, after which I would love to acknowledge our team at CVAI. All right, so why do we conduct research like that? As you have seen throughout this conference and the two presentations before, the evaluation of underlying cortical mechanisms and functions using artificial models is really popular. And throughout the last decade, many artificial models have been proven to be state-of-the-art cognitive computational models. And following that, there has been a lot of research that was able to mimic, predict, and even explain the activity in the visual cortex. We can see an example of it on the right, which is one of the experiments from a study from one of our colleagues, Shitish. He was able to map artificial neural networks trained for different visual tasks to, like, for example, like scene classification and 3D key points to areas of the visual cortex. And he was therefore able to explain the functionalities of different cortical areas. And this basically just shows that this kind of research has the potential to uncover brain mechanisms that are still unrevealed and maybe even open up new avenues for research. And yeah, the most common way to compare model to neural activation is through RSA. But since most of you probably already know what RSA is, I'm not going to go too deep into that. Another rather new way is of aligning the brain to model activation is through linear encoding, where the features are basically linearly mapped onto the fMRI responses. While that is probably all common knowledge here, common knowledge is also that this kind of research has some accessibility issues. Of course, there are difficulties in implementing a baseline for comparison, which can limit the collaboration across the two disciplines. Another problem is the abundance of available DNNs, which can make it difficult to maintain an overview, especially if you want to cater to a neuroscientific research. Additionally, conducting this research can be time consuming, especially if you have to implement everything on your own over multiple runs. And finally, reproducing existing studies in order to build from them can be difficult without an existing baseline, which also can hinder the transparency of those kind of experiments. And yeah, this is where Net2Brain comes into play. So in collaboration with Radosław Ciche's lab, we at CVAI created Net2Brain, a user-friendly toolbox for neural research using DNNs. It basically began as a toolbox for the experiments with our team, but then it quickly became a popular resource for our collaborators as well, which has basically helped them to use deep neural networks in their studies. We are providing an all-in-one solution with over 600 pre-trained neural networks, trained for different visual tasks, and you can even plug in your own model. So this basically doesn't limit you to certain types of architectures. And of course, using this toolbox, you want to make the collaboration of neuro and AI research easier because using this toolbox, non-computer scientists are able to take advantage of these benefits. So what are the key functions? First, the feature extraction of a huge collection of different models, pre-trained or random or even your own models. Then the creation of RDMs, and then finally evaluation using RSA, weighted RSA searchlight, and linear encoding models. So when developing Net2Brain, we make sure to keep an open framework. We don't limit to certain type of architectures. So we also include like video models, multimodal models, and soon even audio models, which could be interesting to look at. They are currently being implemented. And we also want to make sure that the toolbox is easy to use and implement a model selection guide, which I can show you in a second. Also, the extraction functions are flexible, so you can just basically adjust them to your needs. And finally, we wanted to create this bridge between neuro and computer scientists so that users can conduct research really fast and reproduce existing studies and maybe build from them with new hypotheses. And yeah, so if you're interested to test our toolbox, feel free to check out our GitHub. There you will find notebooks that showcase how to conduct experiments with our toolbox. I actually have a notebook prepared for you today to show you some of the main functionalities. This will cover a study, which is actually a study one of our colleagues, Shitish, did a while ago. So what I want to do is the following. In the paper, one of the experiments was to unveil the function of the PPA using deep neural networks. And what happened here is that research suggested that the PPA is a scene selective brain region in the late ventral pathway. And a recent hypothesis in that matter is that it represents structural relationships between scene elements. How do we test if that's the case? We can compare the brain response of the PPA to responses of a model trained for scene classification and a model trained for scene parsing and see which has the higher correlation. As a quick reminder, scene classification identifies the scene by category. So it basically labels the different scene elements. So for a kitchen, pans and cabinets would be contextual cues. So that means as long as there are pans in the stove, it will recognize the kitchen. Scene parsing, however, is a pixel-wise labeling of the entire image. So that means that it encodes spatial organization. So the simple elements are not enough to figure out what is the kitchen. It matters where the elements are located. And since we expect the PPA to encode structural relations, the scene parsing model should have higher correlation to the PPA than the scene classification model. So let's go ahead and test this. I actually wanted to do this on Google Colab, but the internet is not working. So we're going to do it like this. Let me just adjust. Oh, okay, maybe not. All right, so this is one of the notebooks that are available in our repository. There are more notebooks available that show you all the functionalities. This is just an example for this for the study at the moment. So we want to conduct a study, but before I go there, I would like to show you our model selection guide. It's actually big enough for you guys to see. Hold on. Oh, perfect. Thank you. So first, I would like to show you the model selection guide. So I mentioned we have a lot of models available in our toolbox. However, if we go through all of the models and through all the net sets, it's too much to go through because these are just a lot of models. Oh, you might be wondering what a net set is. So basically, we have models from different sources, and it might happen that two different sources might have the same model. So we just grouped into net sets so we don't confuse the models to each other. And because there are too many to go through, we implemented this kind of taxonomy where you can filter through certain attributes of the model. So for example, if you want to look for a model that has ResNet in the name, you can just use this function, look for ResNet-like models. You can also look for models that are trained on the taxonomy data set, which will just return these models. You can look for models that are trained using the Sinclair method. It just basically helps you to find certain models for your research needs. And you can also do a custom search. So if you look for COCO trained models for object detection with the FBN in the name, you can do this. But yeah, talking enough about studies, let's go back to our study. We want to see if the scene parsing model or the scene classification model has higher correlation to the PPA. And for that, we are going to use the dataset by Michael Bonner, which you can just download through the API of our toolbox. We have two additional datasets if you want to play around with, that you can find them in the other notebooks of the repository. So yeah, now we want to load the scene classification model and the scene parsing model into the toolbox. And since they are already implemented, you can just load them up with the by stating the name and the net sets. If you have your own model, however, you can just basically replace the string here and with your model variable and still use the same features of the toolbox. So we have the models now loaded. And if you still want to see how different the models behave, I have some visualization code here. So the classification model returns a tensor, which replies to the ORCID class if we input this image. And the scene parsing model has this pixel-wise labeling here. So this is again for the how these architectures are different. And now we want to extract the layers, and Net2Brain comes with a suggestion for layers to be extracted for the implemented models. So for the classification model, it would be these layers. And obviously, these are not all the layers that can be extracted. These are all the layers that could be extracted. So if you disagree with our selection, you can always plug in your own layers in the extraction function. So this is the extraction function. You can put in a stimuli path, a save format, a save path, and optionally layers to extract. And this will just basically extract all the features for all the layers for every image in the dataset. We have 50 images and 2 models. And now we can use these features and create RDMs out of them using the RDM creator. So we just load up the features we just created, create a save path for the RDMs, and then we will do this. And this will basically just create an RDM for each of the layers available in the model, or like the models you have selected for extraction. And this, and now we can use these RDMs and perform RSA. So we just load up the RSA module, select the model RDMs, the ROI path, and a model name, which is important for the plotting functionality because you might want to have a certain label for your model. So we are going to do this, and this will return two dictionaries, which basically already contain all the information you need. You can already see here that the scene classification model has lower correlation to the PPA than the scene parsing model. But you might be wondering, is it significant? We have a function for that. You can actually load up the scene classification evaluation into the scene parsing model with our compare model functionality, which will print out the significant pairs. And you can already see here the difference is significant, but still you might want to plot it. Fair enough, we have a plotting functionality. You can just basically put in your data frames that we have just created, optionally put up the significant pairs and a metric. I'm selecting R, you can also select R squared. And this will basically return you a publication ready plot where you can see the scene parsing model is significantly higher than the scene classification model. They are both within the noise ceiling, so this is good, but you still might be wondering, okay, isn't this just random? Let's find out. We can always initiate our models with pre-trained equals false. That means that the weights will be randomly initialized. So we can just do everything we just did again, initializing our models with pre-trained equals false, create the RDMs, perform RSA, and at the end, we will have this plot here. I already plotted it. So you can see that the random models are below the noise ceiling and just not as high as the pre-trained models. So let me just go back to the presentation. Yes. Oh yeah, cool. So as you could see, conducting research with Net2Brain is really easy, and it's easy to explore new ways. This is another example that we reported at CCN that shows how Vision Transformer constantly showed incredible performance in correlation to cortical regions. And this, for example, just highlights that Vision Transformer can also be closed models of the brain, which can make sense if you think about it, although it was also surprising for us. And yeah, Net2Brain basically facilitates this kind of research. What are our future plans with Net2Brain? Encoding models, we just added them, so it's more of a present plan. They are already inside of the toolbox. Audio models, however, they are currently being implemented. We are currently also working on code to take in your fMRI responses, like your raw fMRI data, and to directly turn them into RDMs. So you don't have to do this step because it can be tedious. Then more documentation, more example notebooks, and where you guys come into play. We want to get community feedback so we can incorporate your ideas into the toolbox, because this will obviously also help us. Yes, so before we finish this presentation, I would love to introduce our beautiful team. First, we have Professor Dr. Gemma Reuk, who is our lead researcher and professor at Goethe University Frankfurt. Then there's me. My name is Dominik Bersch. I am currently finishing my master thesis and aim to start my PhD in October. And below you can see all the other talented people that helped making this possible. So yeah, that was my presentation. Thank you for listening. I hope you enjoyed it.